Yes, that's right. So 3D joints continued. We went up through what I call joint category 2, which was rollers and pin and slot joints. So now we're on to the third category. There's only one joint in this. So joint. That was all I want to say about it. Okay. Joint category 3. So these introduce 3 variables into Newton's laws. There's only one of them. This introduces 3 variables into Newton's laws. And the only joint of this type is a ball and socket joint. Okay, so it looks something like that. I have one here. So Freebody diagram of that top piece. Has a full vector of forces. And if you think of, a lot of times these are going to be connections between 2 different bodies. Then this is the free body diagram of 1. Sorry, I'm going to erase this. I'm going to call this the force on 1 by 2. And then you could also draw a free body diagram of body 2. And that would be a force vector, force on 2 by 1, which is negative F12. So those forces are equal and opposite. Any questions about that? Now, joint category 4. This is the most complicated one of all of them. Well, 4 and 5 together they have a lot in common. Joint category 4. These introduce, well, it's only one, so introduces up to, and that's where the pain lies, up to 4 variables into Newton's laws. So in other words, there are applications where it doesn't introduce 4 variables, and I need to describe the difference to you. This joint is called a pin joint without thrust. I just spelled without with an S. Without thrust. Okay. That looks something like this. with these two things being connected by a pin. So there's the pin. And the thrust, so thrust is a force vector along the line of the pin that connects them. And so the idea here is that, let me actually draw a little bit of this pin here too. Okay, so these two things can rotate around the pin relative to each other, but they can also slide along the pin relative to each other. You see that? And so this is a good model of a pin joint without thrust. So let's think about what's allowed and what's not allowed. So first, let's think about the forces. Can I pull, so I'm going to think about the base piece is mounted to the ground, and I'm going to think what I can do to this little, the little stick that's attached. Can I translate it in that direction? No. Can I translate it in that direction? No. So we know that we have at least two forces, right? One along this axis and one along this axis. Can I translate it this way? Yeah, that's what the no thrust means. Imagine that being smooth. Okay. So if a force tries to push it that way, there's nothing in here that resists that motion. Okay. So there are two axes of force, but not a third. And what we're talking about there is the thrust. There's no force in the direction of the pin, no thrust. And then what about rotations? It's free to rotate like this, right? Let's call that, I'm going to use the same coordinate system as I did before. So that's a rotation about the z-axis, right? That's fine. So there's no couple applied about z. What about the y-axis right now? Can I twist this around in a circle? No, that's not allowed, right? And then the last one is, can I rotate this around an axis like that? No. So in other words, with this joint, there are two force vectors applied and two couple vectors applied. Those are the four variables that get introduced. And so let me show that first, and then I'll go into the sort of complicated part of this. Okay, so there's a force vector this way and a force vector this way, but not one. Let me do this more three-dimensional. Okay, so those are perpendicular to each other. But there's no force along the axis, and that's also where there's no moment because it's free to rotate about that axis. So there are forces in these directions and also couples in these directions. And those couple components I'm going to represent with those double arrows. Okay, so that's 4. I'm going to put these in parentheses, the couples, because the forces are always there, but the couples are not always there. So let me show why that is. So now, I could have thought of this, and I was talking about it before as if this is a single pin joint without thrust. But you could also think of it as two separate pin joints without thrust, right? One here and one here. And so when we talk about the two moments, that the two couples that this applies, one keeps it from twisting this way, one keeps it from rotating around like this, okay? If one of those joints is the only thing present, then it will prevent those rotations, right? But if you have two of those joints along the same axis, like I have here, it's not actually the ability of one of those joints to prevent that rotation that keeps it from rotating. It's not really the couple applied by this or the couple applied by this. It's the combination of the force applied by this and the force applied by this. So if you ever have a pin joint without thrust, if you ever have two of them that share the same axis like this, then you ignore the couples that one of them is capable of applying. Okay, so so I'm going to write this as I'll call this force X and force Y, and I'll call these couples MX and MY. So I'm assuming that the Z-axis is like this. But notice if you have two pin joints sharing that same axis, ignore those couples. Okay. So in the case of this, where you're thinking about this as two separate pin joints, one here and one here, we would say that each one of those two applies two components of force, but neither of them applies any couple. Okay. Any questions about that? So this is the only time you have to worry about it. If you have two pin joints sharing the same axis, then those couples in parentheses don't show up. Yes? The thrust is, so the difference is this one, the next one we're going to talk about is with thrust. And in this case, there's a flange around the joint that keeps it from sliding this way or that, which means that this joint applies a force along the axis. And a force along the axis like that is called thrust. So one without thrust can do this, and one with thrust is stuck in place. Okay, joint category 5. There's only one of these, and it introduces up to, again, 5 variables into Newton's laws. So this could be a joint like this. It's still a pin joint. But now there's flanges on the two outsides that keeps this from sliding along the axis. So an example of a pin joint with thrust is this thing. Okay. So if this is X, Y, Z, let's first think about forces. Can it translate along the X-axis? No. Can it translate along the Y-axis? No. Can it translate along the Z-axis? This time it can't do that either. So there's 3 components of force that's applied by this instead of 2 components of force. And now we'll think about the couples that it can apply. Can this thing rotate about the X-axis? No. Can it rotate about the Y-axis? Nope. Can it rotate about the Z-axis? That's the one that it can. Okay. So this can apply 3 forces, 3 components of force and 2 components of couple. So free body diagram. We'd have three components of force. And then which components of couple can it apply? Well, the one that it doesn't apply is about the axis, because this thing's free to rotate about that axis. So we could have a couple component that way. That would be my. We could have a couple component that way. That would be mx. There never would be a couple component about the axis. Okay, well, again, those will not be present if you have 2 pin joints sharing the same axis. How did I write that before? So notice, same thing as last time. If you have 2 pin joints sharing the same axis, then you ignore those couples. Yes? Yeah, that's a really good question. So, like in all these examples, I think we sort of have that, like this ball and socket joint, I said it can rotate freely, about any axis, but you can see that it eventually would run up against the side. We don't care about that because we know the position that all of our structures are in at the instant we're analyzing them. So as long as they have a millimeter that they're free to move in any direction, or what I mean, an infinitesimal amount, this still functions as freely rotating. So no, we don't care about that unless in the application that we're using it's jammed up against the side, and then you'd have to model it as a different kind of joint. Okay. Yep. Yeah. So this is an example of a pin joint with thrust without another one there, This is like your knee, So in this case, the joint itself is required to keep it from rotating that way or to keep it from twisting. But in this case, where you have 2 of these pin joints sharing the same axis, it's not one of these joints themselves that is called upon to avoid that rotation. It's the forces provided by both of them together. And the reason that it works that way is that hinge joints aren't very good at applying these couples. They're much better at applying the forces. And so if it can rely on the forces rather than the couples, that's what it's going to do. Any other questions? And then we're down to the last category, so joint category 6. There's one joint of this type. So this, I didn't give the name for this. This is, so this is a pin joint with thrust. As opposed to the one above without thrust. Joint category 6 introduces 6 variables into Newton's laws. And there's only one type in this category. What do you think that is? Yep, like a weld joint or a fixed joint. And so that would be like that's an object that's rigidly attached. And so a fixed joint, there's no motion allowed. So all 3 axes of translation are restricted, and rotation about all 3 axes is restricted. So there have to be 3 forces and 3 couples. And so a free body diagram would have the forces like that. I'll call it R. And then it would have the couples like that. I'll call that M. And if you have a single rigid body, there's no way to calculate the reaction loads applied on the body if you have more than 6 variables in Newton's law. So if you have a fixed joint like this on one end, and then down at the other end you have a pin joint or any other kind of joint, you know. So let's say it's a let's say it's a ball and socket joint, because then we don't have to worry about. There would be 6 variables introduced by the fixed joint. At the ball and socket joint, there would be 3 variables introduced. That adds up to 9, and so there's nothing you can do about that. And intuitively, that makes sense, because what it means is you could remove some of those joints, some of those constraints, and the thing would still be rigid. And so if a 3D rigid body problem has more than 6 variables, the problem is statically indeterminate. It means using the ideas of statics, you can never calculate the external loads. There are ways to do calculations, figure out the loads in statically indeterminate structures, but we're not going to do it in this class. In D form, we'll talk about how you would use what you know about how the material deforms to calculate the loads when something's over-constrained like that. Any questions? Okay, let's do an example. So let's say there's a sign that's attached to a wall. So there's the big rectangular shape. I'm going to move it down a little. Okay, and it's connected to the wall by a pin joint, a ball and socket joint over here. Okay, so that's a ball and socket joint. And if you just tried to connect a shape like this to the wall with a ball and socket joint, it would swing down. So we need something else to hold it in place, and that's going to be done with two cables. One is going to be most of the way to the end, and it's going to connect to the wall over here. And so I'll give you the dimensions. Okay, so this dimension is 1 meter. This dimension is also 1 meter. And then there's another cable that attaches to the end of the sign and goes over to the other side. I'm going to get this over here. Okay, so this distance horizontally is, doesn't look like it, but it's 2 meters. And then this distance up is 1.5 meters. This stuff is so hard to draw and make it look good. Okay, you follow those dimensions. From the one attachment point to the end is 2 meters. And then from the other end to the first attachment point is 0.5 meters. And then the mass of this object is 50 kilograms. And we want to know what are the cable tensions and the loads applied to the sign by the ball and socket joint. Uh, this is something you could easily imagine wanting to calculate for some kind of architectural job or something. You have something like this. You need to know what forces are applied to hold it up so you know what kind of joint to put there, how strong these cables have to be, if maybe there's a way you want to go rather than cables, that sort of thing. So this is a pretty plausible engineering problem. Any questions about the setup? Yes. Oh, that's a good question. 1.5 meters. Okay, so the first step is a free body diagram. So there's the body. And let me give a coordinate system here too. So I'm going to put the origin at this ball and socket joint. I'm going to call that the x-axis. The y-axis is up, and the z-axis is this way. Okay, so at the ball and socket joint, there's a full force vector. That's what a ball and socket joint does. So I'll call that R. From the center of mass, there's a weight force. That's 50 times 9.81, so 490.5. And then there's two cable forces. The one from here that I'll call TA, and the one from here that I'll call TB. In order to figure out how to represent these forces, we know their directions, we just don't know the magnitude. So we're going to have to come up with unit vectors in both of those two directions. Okay. So I think a pretty reasonable first step here is just let's identify all of these points. In our coordinate system, let's just find the coordinates of all of these points, and let's also find the coordinates of where those two cables attach to the wall. Okay, so let me give names to all these. I'm going to call this the point A. It's attached to cable A. This is point B attached to cable B. I'll call this C and this D. And then the center of mass where the weight's applied, I'll call that E. So let's figure out the coordinates of all those points. Okay, so first the point A. So how do you get to the point A from the origin? You go 1 meter in the positive Z direction, and then 1 meter in the positive Y direction. You don't go anywhere X because you started at the wall and you ended at the wall. Please stop me if you have trouble visualizing any of these, and I can maybe explain it a little more. So this point A is 0, 1, 1. And then how do you get to the point B from the origin? We're going to go 2 meters in the negative Z direction, and then 1.5 meters in the Y direction. So B is 0, 1.5 Y, negative 2 Z. What? So to get from, so we're starting at this point, and you go 2 meters in the negative z direction. That's the z component is -2, and then 1.5 meters in the positive y direction. So 0, 1.5, -2. Then the point C, how do you get to C from the origin? 2 meters in the x direction and nothing else. So the point C is 2, 0, 0. How do you get to the point D from the origin? Yep, 2.500. And then the last one is the center of mass. So to the center of that rectangle, you can go, the whole length is 2.5. So half of the length in the x direction is 1.25. So go 1.25 in the positive x direction, and then go 0.75 in the negative y direction, and you're there. No. It's 2.5 divided by 2.
Yeah, you're right.
No problem. That is the first of many times that'll happen this semester. So E is 1.25 in the positive x direction, and then negative 0.75 y, 0 z. Okay, so now we have all those coordinates. And now let's figure out the unit vectors for these cable forces. So a vector that goes, so I'm going to call this UA. Okay, so the first thing we want is a vector that goes from C to A. Okay, so we'll do that as coordinates of A minus the coordinates of C. So that's 0, 1, 1 minus 2, 0, 0. So negative 2, 1, 1. And then the magnitude of that vector is 2 squared plus 1 squared plus 1 squared square root. So square root of 6. And so a unit vector in the direction of that cable, I'll call it UA hat, is equal to negative 2 over the square root of 6, positive 1 over the square root of 6, positive 1 over the square root of 6. And so the force vector that cable applies is this times the variable TA. So negative 2 TA over root 6, positive TA over root 6, positive TA over root 6. And now we need the unit vector for the other one. So we need a vector to start with that goes from D to B. So that's going to be, so I'll call that the vector UB is equal to B minus D. The coordinates of B are 0, 1.5, negative 2. The coordinates of D are 2.5, 0, 0. And so you get the vector negative 2.5, 1.5, negative 2. The magnitude of UB is 2.5 squared plus 1.5 squared plus 2 squared, all square root. So that's 6.25 plus 2.25 plus 4, 10, 12.5. So this is square root of 12.5, whatever that is. And so then the unit vector, UB hat, is equal to negative 2.5 over the square root of 12.5, 1.5 over the square root of 12.5, negative 2 over the square root of 12.5. And so then the force that's applied by the cable B is equal to, well, can someone give me these as decimals? Just each one of these one by one. So negative 2.5 over square root of 12.5. Negative 0.707. And then we're multiplying in the tension TB. .424 TB. Negative 0.566 TB. And while we're doing that, let's do that for the first one too. So what's negative 2 over square root of 6? And then 1 over square root of 6? Okay. Okay, so that was a lot of calculating. Remember where we are in this process? So we still haven't written out that table of the row vectors, the force vectors, the moments. So now that we have all the forces, we can represent them as vectors. I'm going to write out row, force, moment, calculate all those, and we're going towards Newton's laws where we can solve for these variables. Okay, so row, force, moment. We're in 3D now, so we have to write everything as three-dimensional vectors, and we're going to have to represent the moment as a vector too, because we can have non-zero values in every component of the moment. So let's first do the force R. That's a good warm-up one because the row vector is 0. Well, I'm going to put the about point at the origin. Okay, so row vector is 0. The force vector is Rx, Ry, Rz. And the cross product is the 0 vector. And next I'll do the weight. So the vector from when I put the about point at the origin, what I did was make it so that the coordinates of each of these are the row vector to that location. notation, so I don't have to recalculate the row vector. So the row vector for the weight force is 1.25, negative 0.750. And the force vector is 0, negative 490.50. And if you take that cross product, you get 0, 0, negative 613.13. And now I'll do that cable A. So where on here is that cable force applied? What's the location where that cable force is applied? C, that's right. So the row vector is 2, 0, 0. And the force vector is this sort of ugly thing for FA. Negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. And the cross product is 0. And then negative 0.816 TA and positive 0.816 TA. And then the last one is the cable force for cable B. Where's that force applied? D. And so the row vector is 2.500. The force vector is negative 0.707 TB, positive 0.424 TB, negative 0.566 TB. And the cross product is 0, 1.42 TB, 1.06 TB. Okay, so now we have everything we need for Newton's laws. We're going to add up all these forces and set them equal to 0. That's Newton's second law. And we're going to add up all these forces, set them equal to 0. That's the rotational equation. How many variables do we have? Yeah, 1, 2, 3, 4, 5. How many equations do we get here? 6. Is that a problem? That can be a problem, but it's not going to be in any of these problems. What you'll see, I mean, you can see it right here. We're going to do the x, y, and z equations for this, the x, y, and z equations for this, and look at what the x equation for the moments is just going to give us 0 equals 0, so that goes away. And so really we're going to solve a system of 5 equations for 5 variables. Yep. That's right. That's exactly right. Okay, so Newton's law. says Rx, Ry, Rz plus 0, negative 490.5, 0, plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 0.707 TB, positive 0.424 TB, negative 0.566 TB, is equal to zeros. And the moment equation says 0, negative 0.816 TA, positive 0.816 TA, plus 0, 0, negative 613.13, plus 0, 1.42 TB, 1.06 TB, is equal to 0, 0, 0. And there you see this first equation just goes away. It doesn't mean anything. So let's take a minute now. Hopefully a lot of you have calculators, and see if you can go through this with the reduced row echelon form on your calculator. And then I'll come back up here and write the answer down. Shoot. Yeah, number 4, that's a typo. That should say 3D. Okay.